Θα προχωρήσουμε στη δεύτερη μας ενότητα και στο προεδρείο μας βρίσκεται η καθηγήτρια Μαστροτσίκο Μικόλ και ο δόκτωρ Καζάκης.
Welcome back to this section, groundwater, surface water interaction and climate variability. I will give immediately the stage to our keynote speaker, Professor Adriana Bruggeman, who is going to deliver a speech about general perspective on baseflow monitoring, modeling and analysis. The stage is yours.
Yassas, I'm presenting you a few keys on baseflow because I understand we are here in a negative time. So I will keep it short, and we cannot remember everything of all the presentations we see today. But I want to give you a few highlights, and then I'm more of a hydrologist than a hydrogeologist. So I think I'm standing here, it's me against you. But luckily I found some more hydrologists in the audience. But, so it's good to see the perspective from baseflow. Because baseflow is the contribution of groundwater to stream flow. But with this, it also gives you the complete picture of the aquifer system. If you're sampling boreholes, if you're doing borehole pumping tests, you get a local picture, right? But the baseflow gives you the complete picture of the aquifer system. And here I also want to emphasize the sustainability. But you can do a pumping test and find out what is sustainable pumping, but you're taking water out of the system. So what you're taking out of your borehole, it will not come to the groundwater. Right? So this is how we need to consider the whole system. Baseflow is, of course, especially in a semi-arid environment, very important for maintaining the ecology of streams, of ecosystems, of downstream areas. So that's why we would like to have a better understanding of baseflow. So traditionally, we do baseflow separation, but we have observed stream flow records. We try with numerical methods to find the antecedent recession to distinguish the baseflow from the stream flow. Here we see separation with part. It's a very, very popular USGS methods for separating baseflow because it doesn't require any subjective parameters in the system, but it uses a time series, it finds the recession time, and then it makes linear interpolations of the baseflow. We've been trying different methods, and we found that part gives is a very, very good and solid method for separating baseflow. So some of the data I will be showing you next is separated from the streamflow records from the Water Development Department in Cyprus with the part software method. Here you see the streamflow and the baseflow in Perisrona watershed in Cyprus. This is on the northern foot slopes of the Troodos Mountains, coming all the way from Paputsa, 1,540 meters above sea level, to the streamflow station at 430 meters above sea level. On the x-axis, you see the precipitation, annual precipitation over the watershed area from the hydrologic year 1980-81 to 2018-2019. On the y-axis, you see the stream flow and the base flow. The stream flow is, of course, the one on top, and we see that with the precipitation, it has a much more strong signal, so it's much more stronger related to precipitation than the base flow. So when we're having, considering precipitation variability, climate change, we see that the base flow is a much more stable component than stream flow. So this is also the importance of base flow we need for the future. Looking at a few more stream flow stations, you see here the Perisrona station. We have here a few stations on the north, two from the higher elevations, with the ultramafic from the top of Mount Olympus. We have one station in the northeast from the Pedreos River Basin and 2 in the south. When we look at these long-term records from the Water Development Department, again, on the top we see the stream flow on the way from 1975 to 2019, and we see the highest stream flow coming from the top of the Mount Olympus, but as a runoff coefficient, stream flow over rainfall of 0.57. This is really very, very high. And we see here the stream flow in millimeter, annual stream flow millimeter over the watershed. When we look at the base flow index, we see that this highest watershed has an extremely high base flow coefficient, almost unbelievable. It's 0.96, so 96% of the stream flow is a groundwater contribution. It's base flow. And this flows year-round, so it's very stable. But what we also see, that it's stable over time. So none of the lines here you see in this figure showed any linear non-parametric trends over this 40-year time period. So the next highest base flow coefficient comes from Platanistasa watershed, also Platania watershed, sorry, also high up in Troodos with a large percentage of ultramafic geology. The lower base flow coefficient, 50%, is from the Pedreos, and that's mainly diabase rocks. We do have also lower base flow indices in Cyprus, but this is mainly in the lower area, in the sedimentary areas, where we already have lost, again, some of the base flow contribution from the mountains towards the plain. So here we are looking at the base flow indexes on the y-axis, and on the x-axis we see the geology percent over the area of the watershed. On the left top you see the ultramafic, and there you can see again the 96% base flow index. But in general we'll see that the ultramafic, they have higher base flow indexes, but the pattern is not very clear. Again, Gabbro on the top right, also among the higher base flow indices, but it isn't a very consistent pattern. And even a more mixed pattern is when we go down to the diabase, so we see the percent diabase over the watershed, and an extremely variable base flow index from these watersheds. And then the volcanic complex, right, the pillow lavas, for sure, they have lower base flow indices, right? If there's a higher percentage of volcanics, lower base flow index, but it's also influenced by the fact that they are further downstream, right? So, although we can see a pattern, the pattern is not clear. So if we want to try to understand the aquifer system based on the base flow, just looking at the stream flow is not enough. So we want to look at the chemistry, and then here, this is a contribution of Christos Christofi from the Geological Survey Department. Here we're looking at isotopes. This is over 2 years, so we should see 2 different years. There are 6 stations in here. The brown stations are the higher stations, the wet stations are downstream, the midstream stations are the blue one and the black one. So we see differences between the stations, but we also see differences in winter and in summer, a lot more enriched in summer. And we see also the hatched area is the deuterium excess. But we also, in the first year, 2016, we see the effect of the snow melt. So we can get a better understanding by looking at isotopes, but still not sufficient. And then we are looking at auto-sampling, right? And here we look at data from Scotland, from Professor Neil and his colleagues. So they're sampling every 7 hours. We see the nitrate on the left top, calcium on the right top. Right? We see an enormous variability. But for nitrate we can understand because there are also biological processes involved. But if you look at the 4 pictures down on the lower part, those chemistry, the chemicals, even they vary over the time of the day. So we get different chemicals for breakfast, lunch and dinner. Right? And this is caused by biological processes, groundwater types and transpiration, even though the signal in the transpiration as the stream flow totals is much, much less than the signal we find in the chemistry. So we get more information, but still have a very complex and variable picture. So now I will show you the last slide. So this is what the future looks like. But on-stream analysis using an isotope analyzer and ion chromatography with a 30-minute sampling and analysis interval, right, from the stream flow. So even here, and this was done in Switzerland, right, we see the monitoring hut. Even here we get a very, very mixed picture, and still there's a lot of uncertainty. So the more data we have, the more we learn, but still we do not always understand what we are seeing. And then, of course, we would all like to have some station, and that's why I'm showing it here, because I would like to cooperate with all of you to bring this kind of stations to our streams, to get more data, more analysis. We also need, of course, to understand you put your isotope analyzer out in a hut next to the stream. You have to be certain that it will not be stolen, because this reminds me of my time as a PhD student in the United States, when we had sampling huts like this, not with isotope analyzers, but with expensive equipment also, and they would break them open, and what would they steal? They would not steal our $1,000 of equipment, they would steal the car batteries. Thank you for your attention.
Thank you very much for your interesting presentation. I just want to mention to the audience that if you would like to make questions, we have time for questions after the presentation, but you have to reach the microphone, which is in the middle of the stairs. So if you want to ask questions, just raise your hands and reach the microphones. Is there any question? Okay, so we can move on to the next presentation, which is about climate effects on stream flow and base flow from Professor Bruggeman.
Thank you. I would like to acknowledge my colleagues, Corrado Camera from University of Milan, George Cites, who is presenting later today, Marinis Iliadis, also presenting later today, and Hakan Jama, all from the Cyprus Institute. So, climate change projections are showing strong reductions in rainfall, also increases in daily rainfall extremes for the Mediterranean region. The picture from climate change projections is quite clear, but potential impacts of climate change on water resources is much more difficult to understand, especially on stream flow because of the flashy behavior of semi-arid watersheds, difficult to model, and always the scarcity of observational data. It's also a challenge to downscale and bias correct regional climate models at high resolution in a spatially and temporally continuous manner over the watershed area. The objective of the presentation here is to analyze relations between rainfall runoff coefficients and base flow indices in Perisrona watershed in Cyprus, and to model the stream flow of the watershed for the near future, already happening 2021 to 2050, under 2 different climate change scenarios. So the study site, already showed you in the previous presentation, a 78 kilometers square upstream area from 50 meter above sea level to 430 meter above sea level. Geology is gabbro mainly in the upstream area and diabase dominant in the midstream area. Very steep terrain with shallow soils, stony, sandy loam and loam soils. Mainly pine forest and sclerophyllous vegetation and small agricultural areas on dry stone terraces and rural mountain communities in the upstream area of the watershed. Average annual rainfall 620 millimeter per year. Stream flow 12 million meter cube per year. And the stream flow is a key input for groundwater resources of the downstream alluvial river aquifer and the Western Mesoauria aquifer system. So you see here the upstream area of the watershed, in green the pine forest and sclerophyllous formations, in red the agriculture, lighter the broadleaf vegetation, and the rural communities mainly in the upstream area. Reference period 1980-2010, so this is used for the bias correction and downscaling of the climate data. We made 1 kilometer gridded daily rainfall data sets for Cyprus with the Corrado camera. We also made daily minimum and maximum temperature data sets, which we use to compute the Hargraves reference evapotranspiration of every kilometer square over Cyprus. Then we spatially averaged the data over the whole 78 kilometer watershed area from the gridded data. So this is the data average over the watershed, which we use for the downscaling and the bias correction. So for the future, 2021 to 2050, we used two scenarios, RCP 4.5 and RCP 8.5. With RCP 8.5, really the toughest climate change signal, business as usual. Used the 50 kilometer MENA Cortex simulations modeled by George Cetus, and they were statistically downscaled over the area of the watershed. And here you see the stream flow station from the Water Development Department. We acknowledge them for their data and the maintenance of all the data collections of the stream flow stations in Cyprus. We also see that it's a very, very steep environment, and this was in 31st December of last year, where there's a high stream flow event. So this is not what you're seeing here, is not base flow. And then the model, so it's a conceptual 4-parameter model, uses a production store, a routing store, a groundwater exchange coefficient, giving either discharge or recharge losses from the stream, and a unit hydrograph base time in days. We calibrate the model using Ness-Sutcliffe efficiency, both the square roots and the logs, and the relative bias. So we see it's a fairly simple model, but we also see with the daily stream flow data separated in 2 periods for calibration and validation. We get very, very good efficiency. We can have a relative bias of 0 for the calibration, Ness-Sutcliffe of 0.86, while 1 is the optimum, so this is really very good. Validation, where we not tune the parameters anymore, 0.77 efficiency, and a relative bias of 1%. So we see that even a 4-parameter model, we can achieve high efficiency in Tirisrona watershed, but we also found that this is not the case for all watersheds in Cyprus. So then the main message I have below, relative change in rainfall over the watershed. We see that the evaporation due to changes in temperature, it's 3 or 4% under the 2 scenarios. Rainfall here, it's much more, it's 18% under RCP 4.5 and 21% decrease in rainfall average annual over the watershed under RCP 8.5. But we see that this signal, the decrease in rainfall, becomes much worse under stream flow. Here we see 20% decrease in stream flow for RCP 4.5 and 33%, so we go from 21% reduction in rainfall to 33% reduction in stream flow over the watershed areas in already a current future of 2020, 2050. And we see here the results. So we see also the variability in the past. The top figure, we go up to 800 millimeter per year in the wetter areas, and we don't reach this at all, those wet years in the future. And we see also that in the future we have drier years which have not occurred in the past, 350 millimeter over the watershed. So we see there's a similar type of variability, but definitely a much drier future with much less stream flow. In conclusion, we can use a conceptual hydrologic model which facilitates a climate downscaling, because we only need to downscale it over the area, not over the high resolution gridded cells. But we model the climate change impacts for small and medium-sized watersheds. Climate change reductions in rainfall are amplified in stream flow. Projections showed up to 33% reduction in stream flow for 2020-2050 relative to 1980-2010. We have strong annual variabilities which emphasize the importance of groundwater storage for water supply. We also see that these simulations are quite extreme. In one of the later presentations in the same session today, we see also downscaling of other projections. So what we also need to look at the uncertainty using an ensemble of climate change projections to have a better understanding of what the future will bring us. Thank you.
Thank you for this interesting presentation. Do you have questions to ask? Okay, so thanks. We move to the next presentation from Maria Margarita Antona, who will present a speech about the simulating historical, actual and future water balance in mountainous watershed.
Good afternoon, everyone. Before we begin, let me introduce myself briefly. My name is Maria Margarita Antona. I'm a hydrogeologist and PhD student at Luigi Vanvitelli University in Campania, Italy. Today I'm here to talk about the long-term observation data, the importance of them, at simulation models, with an example in a mountainous watershed. So, taking into consideration the increasing water demands, we applied SWOT model in Appel Volturno and Calore basins in Campania in order to investigate the variations of runoff, groundwater recharge and potential evapotranspiration. So, let me give you some information about the study area. The altitude varies from 20 to almost 1,800 meters. In general, the area characterized as Mediterranean with a climate point of view, with intense agricultural activities, mainly in the flat areas and gentle slopes. From the geological point of view, we have alluvial aquifers and mainly karstic aquifers. The soil texture in the Appel Volturno characterized as clay to silty clay, and on the other side, Calore basin, from clay loam to loam. Let's move on to the SWOT setup. So in general, the SWOT model needs basic information for the delineation of a basin into small basins and hydrologic response units. Thus, in the current research, we use land cover, soil texture, and dam layers of data, and climate data and hydrometric data. Let me elaborate a few minutes on this point. So, for the calibration and validation procedures, monthly stream flow data were used of 8 years. Moreover, the historical data and actual data are from 8 and 10 years respectively. About the future climate data, these ones were generated using the RCP 4.5 scenario. Now let's move on to the most interesting part, the results. Take a look on this chart. Here you can see the variations of precipitation, observed flow, simulated flow during the calibration and validation period. In general, the results are characterized as satisfied, while the streamflow chart shows a slightly underestimation. Next, we can see the spatial and temporal variation of the parameters. In the first line, A, B, C figures, you can see the variation of runoff from historical to actual and from actual to future period. You can see a trend of up yaard and down yaard. Next, in this, following also the variations of precipitation in that period. The second line, you can see the recharge. Well, this parameter follows a decrease in the future scenario, which is comparable to the historical one, checking the figures D and F. Next, in the last line, we have the potential evapotranspiration. Here you can see from historical to actual and future scenario, in general, an increase due to the expectable also rise of the temperature the next years. Now, this slide brings me to the end almost of the presentation. Today we talk a little bit about the historical, actual and future water balance simulation in the Appel Volturno and Calore river basins in Campania. Runoff, potential evapotranspiration and recharge parameters were analyzed for the application of temporal and spatial variation maps in order to investigate all of these changes and in general to show the importance of them and the importance of the climate variation in the study area, and finally, in the future, to direct remediation actions. Last but not least, I have to mention that all of this work is founded by University of Luigi Vanvitelli from the program Environment Design and Innovation. Here it's a small amount of the references, and thank you all for your attention.
Thank you, Dr. Antona. Is there any question from the audience? Oh, you are too shy. You have to ask questions. Come on. If you Anyway, even for the people who are attending online the conference, if they want to make a question, they can send a message and we can ask the question to the speakers. So even from the online audience, questions are welcome. So thank you, Marita. Moving to the next presentation, I invite to the stage Dr. Gaiolini, who is presenting a speech about influence of transient boundary condition on the unconfined coastal aquifer budget of Campania region in Italy.
Okay. Good afternoon to all of you. I'm Matteo Gaiolini and I'm an Italian PhD student of the Polytechnic University of Marche region. And the study that I'm going to present aims to assess the influence of variable boundary condition on the numerically calculated water budget of Campania region. The Campania region, as you can see in the picture, is located in the southern part of the Italian peninsula and covers approximately an area of 13,500 square kilometers. Its lithological and structural complexity controls the variability of the hydrogeological settings. The study area comprises only the unconfined aquifer and extends from the Tyrrhenian Sea up to 50 kilometers inland, while southward it is delimited by the Cilento mountain range. The flow simulation was carried out via processing ModFlow using the ModFlow 2005 code. Here you can see a three-dimensional sketch of the model domain that consists of 656 rows, 335 columns, and 3 layers with variable width and thickness. Initially, a steady-state simulation was carried out. Then, in order to consider possible changes in the groundwater system, a transient simulation was carried out over a simulation time of 15 years, from the year 2000 to the year 2015, considering 64 stress periods of seasonal length, subdivided in 3 time steps of 1 month each. In order to represent the morphology, a digital terrain model was considered with a spatial resolution of 20 meters per 20 cells. The hydraulic conductivity, together with the pumping wells rate and the pumping rates, and the pumping wells depth, was estimated through permeability tests using 91 boreholes available on the ISPRA database. The MODIS products were questioned in order to obtain evapotranspiration rate trends, while the evapotranspiration extinction depth was derived merging the land use and the soil texture maps via GIS. The groundwater recharge has been extracted from the output of a grid-based global hydrology model and then processed in Python in order to obtain spatially interpolated values. A transient fracture aquifer database was inserted into the model by considering the average measured river stage variation, and this river stage variation dataset was downloaded from the Civil Protection Agency website of the Campania region. Finally, a Tyrrhenian sea level change dataset was downloaded from the Copernicus platform and then elaborated follow the the ISPRA available database for the Napoli, Salerno, Gaeta, and Palinuro marographs. This transient model, considering all these transient datasets as variable boundary condition, was then compared with a base version of the model, considering a uniform extinction depth, a constant inflow from the fracture aquifer, and a constant river and sea level. In order to understand and to investigate which one of these datasets played a major role in influencing the budget, a series of different scenarios have been considered and compared to the transient model. Here you can see a scenario considering a uniform extinction depth, a one considering a constant inflow from the fracture aquifer, a one considering a constant river level, and finally the one considering a constant sea level. Here you can see the model performances for the calibration performed via PEST against a piezometric map for the year 2000. The head scatter diagram shows a good coefficient of determination of 0.94. The calibration was performed against a secondary elaboration of a piezometric map for the year 2013, and in this case, the head scatter diagrams shows a coefficient of determination of 0.92. The volumetric water budget of each component was calculated by means of the zoom budget routine. Here you can see the evapotranspiration flow in cubic meter per second over as the simulation time. The flow has been calculated for the base model in red, for the transient model in blue, and for the model considering a uniform extinction depth with the dashed green line. As you can see, it is possible to see clearly the seasonal variability of the flow, and the fact that the base model and the uniform extinction depth model shows the same flow means that the extinction depth dataset played a major role in influencing the budget. Here you can see the inflow from the fracture aquifer also in cubic meter per second, and the same color has been used for all the components. The flow is lower with a mean value of 2 cubic meter per second. Here you can see the river inflow and the river outflow that represent the river groundwater interactions. They both has a mean flow of around 9 cubic meter per second, and they show no differences between the model. Finally, you can see the seawater intrusion with a very low flow that can be considered also mostly negligible, and the submarine groundwater discharge that shows no changes between the models. Also, comparative analysis has been performed, and the mean flow of each water budget component has been calculated. In this table, you can see the mean inflow and outflow of each component for the base model and from the transient model. Highlighted, you can see the most important contribution represented by the recharge component and by the evapotranspiration component that shows also significant change passing from the base model to the transient model. The same has been done for all the other scenarios. Here you can see the scenario with a considering a uniform extinction depth compared with the transient model that shows almost the same change in the evapotranspiration flow, confirming the fact that extinction depth is a very important parameter that influence most the water budget. All the other scenarios, here you can see the constant inflow from the fracture aquifer doesn't seem to affect a lot the water budget, and there are no significant changes with the transient model. Here you can see the constant river level scenarios and the constant sea level scenario. So to conclude, as we expected, the transient input dataset differently influenced the water budget, and in particular, importing transient river and sea level dataset does not affect the calculated water budget, and therefore simplified model can be considered. The most important impact, as I said, is given by the evapotranspiration extinction depth dataset. Moreover, the total volumetric flow budget highlighted the pivotal role of both the recharge and the evapotranspiration component. So their pattern throughout the simulation should be precisely estimated. Thank you for the attention.
So thank you, Mattia, for the presentation. I guess there's no question. So I can move on to the next presentation from Dr. Zitis, okay, that will deliver a speech about future extreme precipitation trends in the Mediterranean.
Okay, good afternoon, everyone. My name is George Zitis. I'm a geologist and climatologist working at the Climate and Atmosphere Research Center of the Cyprus Institute. And today I'm going to talk about future extreme precipitation trends in the Mediterranean. And before starting, I would also like to acknowledge my co-authors, the co-authors of this study, Professors Adriana Bruchemann and Professor Jos Lelveld. So the motivation behind this study, we see from observations a recent accelerated warming in the Mediterranean. And according to future projections, this warming in the region will continue for the next decades, as you see in the upper plot. And according to model projections, we see that this warming will coincide with changes in the hydrological cycle, mainly expressed as precipitation decreases and manifestation of droughts. And while we know that for temperature projections, these are characterized by high levels of intermodal agreement and significance, this is not the case for precipitation, where the intermodal spread and the robustness and significant levels are quite low. And this is particularly the case also for extreme events. So objectives of this study are to assess the direction and significance and intermodal agreement of the 21st century projections of precipitation extremes in the Mediterranean. We also aim to investigating the changes in the 50-year and 100-year extreme events between recent past reference period and the 21st century. And we aim in approximating the time of occurrence of these very extreme events, the 1 in a 100-year events. And also we would like to see the contribution of daily extremes to the annual total precipitation budget. We have used the state-of-the-art, the current state-of-the-art in regional climate projections, and this is the Eurocordex ensemble. These are available at 12 kilometer spatial resolution, and we have selected a subset of Eurocordex that provides daily precipitation data from a period from 1951 to the end of the century. And we have also selected to analyze the business as usual pathway, which is also known as RCP 8.5. And out of the broader European domain, we have cropped the dataset to cover the Mediterranean. And these criteria that we have set have resulted in a number of 33 climate simulations. We have worked with some precipitation indicators. Of course, we have the annual total precipitation. We have analyzed also, we have extracted the maximum daily rainfall for every year of the analysis. And we have also calculated the ratio between these two variables, the ratio between the extreme daily rainfall and precipitation, annual precipitation total. For the assessment of the significance of trends, we have applied the Mann-Kendall test and the sense slope estimator for the direction of future trends. And we have also applied the extreme, generalized extreme value distribution for fitting the data of the historical period in order to get values, precipitation levels for different return periods. So let's move to some of the results. Here is the intermodal agreement on the left for extreme daily precipitation. So this is the agreement of 21st century trends. And we see that we see a very distinct north-south gradient in this analysis. So for the northern part of the Mediterranean, we expect to see the models tend to agree in significant positive trends. There is an absence of trends in mid-latitudes over the Mediterranean. And on the other hand, we see some significant trends of extreme precipitation in the southern part of the Mediterranean and mainly some Northern Africa territories. And we can compare this figure. On the right, we see the same figure, but this is for the annual precipitation. And for the annual precipitation, we see a very strong manifestation of significant declining trends. And again, there's a hotspot of negative trends in Northern Africa. Here we present the 1 in 50-year extreme daily precipitation event in the left column, and for the reference period, and the projected changes for the first and the second half of the 21st century. And so these are the absolute maximum events, and we see that despite the negative trends that we have seen in the previous maps, we do expect some increases in this absolute extreme rainfall, and this is mostly the case for the second half of the 21st century. And it's not very clear here, but most of these changes are also statistically significant. On the right column, we see the same plots, but for the annual precipitation total, and we can see that in the regions that we expect an increase in the absolute maximum events, we do expect mostly a decrease of annual rainfall, and the signal here is not always statistically significant, with the exception of some regions in Northern Africa and Eastern Mediterranean. Here we have compared the model-derived 1 in 100-year events that are the result of the fit of the GEV distribution on the red box plots, and the absolute maximum rainfall that is derived from the 100-year simulations, projections, which is the blue box plots here. And these are results for different precipitation classes. I have not explained this, but you can get an estimation of the 5 classes. And what we see here is that the projected maximum rainfalls that are derived from the 100 years projections for the futures are higher than the ones that are derived by the generalized extreme value distribution. And here's an example for Levkossia and Cyprus. We can see the return periods, different return periods for the fitted data that are the result from the reference period simulations. And if we take the absolute maximum of the 100-year projections, we see that this is substantially higher. Finally, we have assessed the contribution of the wettest day per year to the annual precipitation budget, and we see it here for the reference period, and particularly for parts of Northern Africa. There is a great contribution of the most rainiest day in the year in the total precipitation budget, and about this value can be higher than 50% of the annual precipitation budget. And here we see the projected changes of this value for the first and second halves of the 21st century. And we do see that for Northern Africa particularly and other parts of the Mediterranean, we expect an increase in the contribution of the wettest day per year to the annual total precipitation budget. To conclude, we have seen a very strong north-south gradient in the Mediterranean daily rainfall extremes, with significant decreasing trends in the south and significant increasing trends in the north. Despite the contrasting future trends, the absolute maximum events are projected to increase in the 21st century, and these increases will be up to 100%. The 100-year extremes that were derived from traditional extreme value approaches, they tend to underestimate the magnitude of extremes if we also consider the effect of climate change. And this is about 20 to 30, this underestimation ranges from 20 to 30%. We have seen that the contribution of the wettest day per year to the annual precipitation budget is expected to increase throughout the region. And the projected increase in extremes, we can conclude and say that these strong reductions in mineral precipitation in the drier parts of the Mediterranean will possibly amplify the challenges of water resources management, particularly for the arid part of the region. And if you would like to see more information, you can access this relatively recent study of us in the Weather and Climate Extremes journal. And here I would like to thank you for your attention.
Thank you. We have to move to the next presentation from Veneziano.
Good afternoon, everyone. My name is Giulia Veneziano, and I am presenting you the work with the title, The Investigation of the Potential Climate Change Impact on a Coastal Aquifer. This work is being part of my PhD thesis and was conducted in collaboration with Professors Voudouris Konstantinos, Anaglostopoulou Christina, and Lukas Athanasios. As it is well known, the assessment of the climate change impact on hydrology has been accomplished by coupling the hydrologicals, and climate models. However, until now, dealing with the climate change impact studies on hydrological is still a scientific challenging issue, due to the uncertainties of climate models and to the various hydrological input data, especially when applying hydrological models in engaged areas. The object of this work is to reasonably estimate the potential climate change impact on a coastal aquifer. In order to achieve this task, a comprehensive methodology is introduced, including two major steps. The first one regards the processing of the climate data used to drive the hydrological models, and the second one regards the hydrogeological simulation of a coastal aquifer under different climate change conditions. Let's know a little bit the research area. It regards a coastal aquifer being part of the Havrias River Basin, located in Chalkidiki, in North Greece. The coastal aquifer is unconfined and is developed into alluvial deposits, lacustrine and lagoon sediments, red clay, and basin conglomerate series. The surround area of the aquifer is covered by metasedimentary rocks, philites, recrystallized limestones, pyroxenites, and dunites. The major crop are the olive groves, and we should note that the groundwater is used to cover the irrigation purposes. Let's continue with the climate data used to drive the hydrogeological model. In this study, the ERA interim reanalysis data used as the reference data. They include daily precipitation, temperature, wind speed, dew point, solar radiation, and albedo, covering a period from 1981 to 2000 and the period from 2016 to 2017, which corresponds to the period with the available hydrological and hydrogeological observed data. The spatial resolution of the area interim is 12.5 kilometers. In order to investigate the future climate condition of the aquifer, the regional climate model enforced by the General Circulation MPI under the RCP 8.5 was used. Due to the initial differences between the area interim and the MPI data, the spatial temporal creaking was applied into the REXEM output by using the symmetric covariance model for the reference period. As you can see on the diagrams, the application of the spatial temporal creaking led to the improvement of the climate model's output, especially in the case of the precipitation. Move on to the second part of the methodology, namely the hydrogeological simulation. The first step of the simulation is to schematize the aquifer using a conceptual model. The piezometry of the dry period of 2016 was used as the initial condition, and the boundary conditions were defined from the lithological profiles and the available geological data. The groundwater abstractions are equal at 6 million cubic meter per year. Regarding the recharge, the aquifer is mainly recharged by the infiltration, the irrigation returns, and the infiltration through the Havrias River basin. Based on the discharge measurement, this infiltration is about of 60% of the surface runoff. In this study, the recharge was quantified by using the ArcSwot interface. The ArcSwot model initially was derived by the area interim data for both the reference period and the period from 2016 to 2017. Based on the ArcSwot results, 19% of the mean annual precipitation is infiltrated into the coastal aquifer. Then we use the ArcSwot results to drive the mode flow model in both steady-state conditions and transient conditions. The calibration was done via the trial and error process. As you can see on the piezometric map and the QQ plot, the simulated and observed hydraulic heads are in a very good agreement. As you can see on the QQ plot, the values are very close to the diagonal line. Similar results are under the transient conditions. The statistical methods show the accuracy in simulation. Then the coastal aquifer was simulated under the climate change condition. In this case, we use the ArcSwot model forced by the interpolated MPI output in order to quantify the future recharge of the aquifer. The precipitation decrease and the temperature increase resulted in the reduction of the coastal aquifer. This reduction is estimated to be equal to 15%. These results were again used to drive the mode flow model. As you can see on the diagrams, a continuous decline in water level is estimated. On the map, you can see the differences between the 2017 and 2019 on the coastal aquifer. And the largest differences in hydraulic heads are observed in the north part of the aquifer. To conclude, the mud flow is capable of simulating the hydrological conditions of the coastal aquifer. The accuracy of simulation was confirmed by the statistical evaluation of the mud flow simulated against the observed piezometric data for the period with the available observed hydrological data. The climate change impact analysis revealed that the temperature increase and the precipitation decrease causes a reduction in recharge. The groundwater simulation indicated that the reduced infiltration resulted in the groundwater level until the end of the 21st century. And last but not least, the estimated decline of the groundwater level implies the decrease in the water resource availability and the seawater intrusion causes the qualitative and the quantitative deterioration of the aquifer system. Thank you for your attention.
The next presentation from Dr. Lazoglu will be on a copula-based approach for the bias correction of daily precipitation in Cyprus.
Good morning. Good afternoon. Can I start? Good afternoon to everyone. My name is Georgia Lazoglu, and today I will present my study entitled A Copula-Based Approach for the Bias Correction of Daily Precipitation in Cyprus, in collaboration with Dr. George Zitis and Professor Adriana Brueggermann. So climate model outputs are used as inputs to impact models. These applications include energy, crop, or hydrological modeling. But due to the model deficiency and the stochastic nature of climate model processes, these outputs tend to present systematic deviations from the real observations. These deviations are known as biases and are extremely important when we are talking about extreme events. So the minimization of these biases is known as bias correction or bias adjustment, and several statistical methods have been developed in order for the minimization of these biases. With this study, we have developed and evaluate a copula-based statistical model for a bias correction of model daily precipitation in Cyprus for a recent past and future time periods. In this attempt, we have several challenges. First of all, the stochastic nature of the variable that we are trying to bias correct was a severe challenge. We are talking about precipitation, and all of us know how difficult it is to simulate and to predict precipitation, especially when we are talking about daily precipitation, and the temporal resolution of our data was another challenge that we had to face. Finally, we had to face a challenge that was that we have a low dependence between the simulated and the observed data set. So the data that we use data from two sources. Firstly, we are using as a reference data set the CY observation, which is a high resolution data set derived from a dense network of stations. This data covers a time period from 1981 to 2010, and the spatial resolution was 1 kilometer. So we are talking about 6,090 grid points. The second data set that we use came from two Eurocordex regional climate models. This data covers the time period from 1981 to 2010 and the future period from 2031 to 2060. This data had a spatial resolution of 12.5 kilometers, and we are talking about 39 grid points. You can see these points with purple bullets in the map. Before continuing to the methodology that we have used, I would like to spend some time in order to explain you what is the main tool of this presentation, which is copulas. Copula is a mathematical tool that can describe the dependent structure between two or more variables that may have different marginal distribution. So, assuming that we have two variables, x and y, and f and g are their marginal distribution, then there is a unique mathematical function, a copula family, that can describe the dependence between these two variables. And the main advantage of copulas is that can give us information, a mathematical model, between variables that may have no correlation. So in these maps, in these graphs, you can see, in these graphs, you can see that we have two variables. The first one is fitted by the normal distribution, while the second one from the gamma distribution. If we're trying to find the linear correlation between these two variables, we will have zero correlation. But if we are using copulas, then we will notice that there is a strong dependent structure between these two variables. So we have used this tool in order to develop a copula-based structure scheme between the reference and the simulated dataset using information from the historical periods. This procedure was followed for every grid point separately. In order to increase the accuracy of our results, we propose to use this this tool separately for the two hydrological periods and separately for extreme and not extreme events. As extreme events, we use all the data that exceed the 0.9 threshold, percentile as threshold. So the results for the recent past period, in these graphs you can see the results for each grid point. With the gray line it's the reference data set, with the red line it's the model data, and with the blue line it's the bias corrected data set. So as you can see, there is a great improvement for both models. The improvement for the first model reaches the 85%, while for the second one, the 92% of the grid points. The initial absolute total biases for the first model was 17%, while for the second, almost the double. But after the bias correction, these biases has been reduced to 3% and 7% respectively. For the future time periods, you can see the monthly results for the two models. And we noticed that there is a decrease in the total precipitation for Cyprus according to both models. The total amount of according to the first model was 415 millimeters for Cyprus, while for the second 280 millimeters. And I would like to mention that the second model is a model that significantly underestimates both the rainy days and the total precipitation for Cyprus. But the climate change signal remains uncharged after the application of the bias correction method. To sum up, in this study, we demonstrate the application of a novel copula-based bias correction method optimized for the daily precipitation in Cyprus. In order to increase the accuracy, we propose to apply this method separately for the two hydrological periods and for extreme and not extreme data. The copula method seems to be able to correct the climate model output regardless of the nature of this presentation and regardless of the nature of the climate model. When I'm talking about climate model, I'm saying that despite the fact that the model overestimates or underestimates the precipitation, the accuracy of the simulated precipitation has been increased to 14% and 28% according to the two models. And we propose the copula as a useful tool for bias correction of simulated daily precipitation of areas with complex topography such as Cyprus. Thank you very much for your attention.
Thank you. Now we have to move to the last two presentations, which will be held online. So the next presentation from Luludis It's about spatiotemporal analysis of a mined out pit lake considering land repursuing.
Lignite industry decommissioning is followed by land and water use repurposing. Thus, coal phase-out era is one of the most characteristic ever-changed environment. Changes in groundwater resources must be seriously considered in the metal-lignite phase. The research area of Kardia mine that we refer to is in South Royal Maize Lignite Bearing Basin, Sarigon named, in Western Macedonia, Greece. Public Power Corporation has developed great mining activities to provide lignite to power plants electric generation. One of these mines is Kardia Field. The hydrogeological basin Sarigol that belongs Kardia Field is surrounded by Vermion, Skopos, and Dacian mountains, and Komanos Horst. New projects are planned to realize after lignite industry decommissioning projects that follows land repurposing. In future states, there will be photovoltaic parks, industrial zone, garbage depositions, lakes, recreation parks, forests, into the area of exhausted mines. It is the intention of PPC to develop and control the evolution of pit lakes in the voids left behind by coal phase-out. As main priority still remains the protection of the natural already existing lakes as Kimaditis, Zazari, Petron, and Vagoritis. In the frequency histogram of Kardia mine digital elevation model, there is clearly a dominant place with a large plain area corresponding to internal waste dump. As a photovoltaic park of 150 megawatt is proposed for these elevated waste dumps, the lake is not allowed to arise above the altitude of 650. A secondary in surface magnitude but flatter plane with slope less than 10% allows swimming. In the range location north and east area of the lake, can be developed a park for water activities, forest camping, and road access network to the beach. The Sulu River is the main river outflow from the basin towards Vagoritis Lake to the north. The recharge area of Sarigol Aquifer is Vermion and Dacian foothills conglomerate talus cones. The predominant direction of flow in the Sarigol Aquifer next to Kardia mine is west to southeast, but exactly next to Kardia open pit is south to southwest. NTVI distribution remote set it at 2020 made feasible the determination of following parameters: soil moisture index, consequently the field capacity of unsaturated zone, annual percolation rate, and water table decline rate annually due to irrigation demands, which is covered by well pumping water. Here you see the annual percolation rate spatial distribution in the area of Kardia mine. And here we have the deficit of groundwater distribution in millimeters. One beneficial land use repurposing is the construction of an hybrid power hydro storage facility, HPHS. The HPHS facilities consist from lower reservoir, upper reservoir, and subsurface power tunnel, and pump motors and generators. It is the principal support for the renewable energy researches, the energy storage concept that water is pumped from the lower basin to be stored to the upper basin in order to be released by downstream flow whenever there is a shortage of electricity on the grid. In the case of green power excess over demand load, this surplus is stored by pumping it from the lower basin to the upper basin. Conversely, when there is a deficit of grid power against energy consumption demands, downstream flow energy from upper basin reservoir to the lower reservoir is released to reinforce the grid. The energy consumption demand between two levels with a height difference is given by Fowler equation. There is a basic difference between PHS in a dam and the HPHS in a remnant open pit. The daily fluctuation of the water level in the lower basin cannot exceed 2 meters. Since the lower basin and the remnant open pit HPHS is not concrete covered pit lake, thus there is very much weathering, erosion, and corrosion impact on the benches that can lead to failures. From this point of view, a range between lower reservoir altitudes of 547 and 580 are quantities for the HPHS optimum operation. Problems with low stability also cause limitations on the absolute level of lake's water level. Water levels under 547 endanger risk of failure with safety factor less than 1.4 in the internal west dam benches. The prediction of the spatiotemporal evolution is crucial for the financial efficiency of HPHS. There are three components of inflows into the lake's water body: surface runoff, lake's water losses, and groundwater seepage phase erosion. The filling of the water lake model is sensitive to runoff. That's why the runoff coefficient in the interior of open pit was evaluated by curve number 2 distribution. A neural network autoregressive model has been implemented in order to predict the future runoff component of inflows and future lake surface water balance losses.
You have to proceed to the conclusion. The time is nearly over. Thanks.
Lake evolution at different years, and it's obvious the groundwater of the open pit sample quality is good to permissible for irrigation purposes. In order to proceed in future water quality prediction, there is a need of having an assessment of future evolution of lakes epilymnion, metalimnion, and hypolimnion. Coming to the conclusions, it is obvious that despite the decrease of precipitation in future and decrease of lakes surface losses in future, the natural filling of the lake is feasible. There are adequate water researches for artificial filling as well from Sulu River. The option of PHS with bigger head difference seems to be more financially beneficial. There is a potential acidification caused by pyrite oxidation. At present status, there is no eutrophication, there is no contamination with industrial pollutions, there is no salinization by high saline groundwater, there is no infection by imported pathogens via river water, which in turn was impacted by wastewater. Thank you for your attention. At your disposal for any questions.
Thank you for your presentation. Is there any question?
Μ' ακούτε, κύριε Λουλούδη? Ωραία. Θα ήθελα να κάνω μία ερώτηση εγώ. Επειδή γνωρίζουμε στην περιοχή και υπάρχει και το ιστορικό με το φράγμα του Περδίκα, όπου είχαμε μία αστοχία, εξαιτίας του γεγονότος ότι έχουμε το βαθύτερους καρστικούς υδροφορείς. Επίσης, η περιοχή εκεί πέρα τροφοδοτείται και ο βαθύς καρστικός υδροφορέας, όπως γνωρίζουμε, εκφορτίζει και όσοι δεν το γνωρίζουν, εκφορτίζει και καταλήγουν όλα αυτά τα νερά σε μεγάλες ποσότητες, από τα οποία υδρεύεται η Θεσσαλονίκη. Τι ενέργειες ή τι ακολουθείτε σαν επόμενα βήματα, καθώς από ό,τι καταλαβαίνω προτείνεται να γεμίσουν τα ορυχεία με φυσικό τρόπο με νερό και παράλληλα να εκμεταλλευτεί και για παραγωγή ενέργειας. Αλλά τι ενέργειες, τι δράσεις θα γίνουν τόσο ώστε να προστατεύσουμε την υδροδότηση της Θεσσαλονίκης αλλά και της ευρύτερης περιοχής. Και όσον αφορά το θέμα της ποιότητας του νερού, υπάρχει περίπτωση όλη αυτή η δραστηριότητα να επηρεάσει και το βαθύτερο καρστικό υδροφορέα? Ευχαριστώ.
Για την περίπτωση του λιγνητορυχείου Καρδιάς και της λίμνης της Καρδιάς δεν έχει καμία σχέση ο καρστικός υδροφορέας, ούτε υδραυλικά στα υψόμετρά του, βρίσκεται περίπου στο υψόμετρο των 350, το απόλυτο υψόμετρο 350, και δεν έχει καμία σχέση με το υψόμετρο του υδροφορέα που τροφοδοτεί τη λίμνη, που είναι στα 640. Είναι εντελώς διαχωρισμένοι οι υδροφορείς, δεν υπάρχει κανένας φόβος για τον καρστικό υδροφορέα. Τώρα για τους regional υδροφορείς της περιοχής, γίνονται μελέτες και παίρνονται τα απαραίτητα μέτρα ώστε να μην υπάρχει καταρχάς, αν γίνει η τροφοδοσία της λίμνης τεχνητά με νερό, να υπάρχει το απαραίτητο υδατικό δυναμικό και να μην στερεθεί η υδρολογική λεκάνη της Αργιόλ. Και κατά δεύτερο λόγο, επειδή θα συνεχίσει να γίνεται η υδραυλική προστασία του ορυχείου ακόμα και όταν υπάρχει η λίμνη, δηλαδή θα υπάρχει ένα πλεόνασμα νερών το οποίο θα πρέπει να απορριφθεί στο Σουλού, αυτό το πλεόνασμα να είναι κατάλληλο και να μην ρυπαίνει και να ακολουθεί τις προδιαγραφές που έχει το Σουλού και η Βεγορίτιδα. Δεν ξέρω αν σας κάλυψα. Δεν ξέρω αν σας κάλυψα με την απάντησή μου.
Μας καλύψατε, είναι μεγάλο το ζήτημα φυσικά, θα συζητηθεί νομίζω και περισσότερο στο μέλλον και θα χαρούμε έτσι να βλέπουμε τα αποτελέσματα της έρευνας να δημοσιεύονται για να καθησυχάζεται και η τοπική κοινωνία αλλά και η ευρύτερη κοινωνία.
Okay, thank you very much. Now we move on to the last presentation, which will be online as well, from Yayawi. The speech will be about the importance of vertical groundwater flow as a discharge component in transboundary CHOTS in western Tunisia.
Good afternoon to everyone. First of all, I would like to thank the organizer of Cyprus conference for the chance to share my work, importance of vertical groundwater flow as a discharge component in transboundary shots in western Tunisia. The most common thinking about the Sahara Desert is there is just sand, maybe for rally. In fact, the groundwater is being used in agriculture. You can find in this picture how the farmers use the old method of irrigation since Roman settlements, and now is used by oil industry. Look at this picture. It appears a flow system or a discharge area of two flow systems, which the water, quality of water and the color is contrastly different. So each picture indicates the importance of groundwater, and the lack of water beneath the Sahara Desert is not true. The content of the talk is an introduction, put forward nature of the analytic system. We see briefly general water balance. We take chemistry and hydraulic response, last but not least, groundwater discharge, and finally, concluding remarks. In this work, we try to find evidence of a vertical component of flow in Tunisia. We want to identify regional groundwater flow with the water chemistry on the shots by recognizing the hydraulic response of the shots, and to show the importance of vertical flow in hydraulic head distribution, which the hydraulic head should be measured in the bottom of the system. We find an observed criteria used in scientific studies related to shots in Tunisia. Study areas are always a section of the whole groundwater system, which they neglect the flow around, and they don't consider the vertical component of flow. Tunisia is located in North Africa, as we know, in the southern place. We will draw the attention of the discharge area, which it is called the shots. It represents the important lakes in Tunisia. In temperate climate is equivalent to wetland. The main distribution of groundwater beneath is present in the map, and the cross section it represents the important stratigraphic information, which basement rock is not shown. What do I mean by not shown? The northwestern Sahara Aquifer system, which it is composed of plio-quaternary, complex terminal, and continental intercalary. Below continental intercalary, there is no stratigraphic and basement rock information. So if you want to analyze the flow system, the line below the third section is basement rock. So flow system is based on the position of basement rock. Why the shots are important? The northwestern Sahara Aquifer system covers a surface of 1.1 million square kilometers. When it is compared with the Guarani Aquifer, which it is 1.2 million square kilometers, we see in the storage of northwestern Sahara Aquifer system is larger than the amount of Guarani Aquifer with an effective porosity of 5%. On the other hand, the groundwater extraction decreased the water level in complex terminal and continental intercalary, and now withdrawal is close to 75 cubic meters per second. In the map below, the water table distribution suggests that the flow is moving horizontally because they don't consider the fluid potential by Hubbard in this attached equation that considers the weight of density of water column, which varies according to salinity and the temperature of the groundwater. Therefore, the groundwater direction proposed by the TDS is different to that suggested by the water table direction. The isotopes tell the story of the storage water in both the complex terminal and continental antarctic layer, suggesting that the water has been strongly evaporated, but groundwater has been collected in the discharge area. However, the recharge areas have not been correctly defined, and the groundwater samples do not represent the actual recharge condition. Therefore, the Thoth section or the Thoth groundwater flow system are required to be taken as a guide for further studies related to the recharge condition. That means most samples collected close to the shores provide information, the discharge condition, meaning the recharge in previous times, but they don't give data on the actual recharge condition.
Sorry, you have 2 minutes left.
Okay. As an overall, the actual geological framework is the base of hydraulic head analysis, classic water balance and flow computation, and the term to understand the hydrogeological response. The pure horizontal flow, it could not be the vertical component of groundwater flow. Temperature, chemical, and isotopic characteristics is important to analyze the regional groundwater flow. And finally, discharge, transit, and discharge will be more understand of the flow mechanism. Thank you for your kind attention and bon appétit.
Thank you very much. Θα καλέσουμε τον κύριο Παναγόπουλο Ανδρέα για να μας κάνει μία ανακοίνωση.
Πολύ ωραία. 2,5 χρόνια πίσω, 2.5 years ago, sorry, I got mixed up. A project called MEDSAL started up with several coordinators, several partners across the Mediterranean basin. It was one of the projects that suffered due to the COVID, but nevertheless it gave fantastic results so far and a very wonderful collaboration. A fruit of this project is a summer school which is organized in the end of June this year, hosted by Bari Polytechnic in Italy. And it's a golden opportunity for all those of you young researchers that would like to get hands into the latest state-of-the-art tools and methodologies into salinization problems, identification, assessment, monitoring, and so forth, and modeling. So this is just to let you know that this goes on. Sorry for the resolution, it doesn't look very well. Actually, you are the first audience to see this because we're getting officially on the air in the next couple of days. So please have it in mind. Keep in mind the word MEDSAL. Try and find our site and try to enroll. You won't lose. It's a 4 days fantastic meeting in a very nice place of the Mediterranean with most of all very important topics delivered by very nice and very well educated and trained and worked people on the subject. And the next one, please. Towards the end of this project, MEDSAL, along with the sister project, which is called Sustain Coast, also working on salinization issues and more on the management issues of coastal aquifers. We're organizing our closing conference in another fascinating city, in Chania, the island of Crete. This is an event to take place in the end of September. Again, another opportunity to join together and exchange views and points and listen to what these two projects have to offer to the scientific society. Both of the projects, of the events, are going to be hybrid, so in person and also through the internet, through a platform. Considering the first one, the summer school, please keep in mind that because of the nature of the summer school, it's going to be constrained to only 20 people following in person and 30 people on top of that via a platform. But there is an unlimited ability to host stakeholders representing bodies from all over the Mediterranean if they want to follow the theoretical part of the courses. So that's all from me. Thank you very much and look forward to receiving your applications and seeing you there. Thanks. Thank you.
Σας ευχαριστούμε πολύ. Τώρα θα διακόψουμε για να περάσουμε και στο διάλειμμα όπου υπάρχει γεύμα. Θα ήθελα απλά να σας θυμίσω ότι έχουμε παράλληλα και την παρουσίαση των poster, όπου όσοι δεν έχετε προμηθευτεί μπορείτε να μας βοηθήσετε για να διαλέξουμε το καλύτερο poster και στο τέλος του συνεδρίου να δώσουμε και ένα βραβείο για το καλύτερο poster. Επίσης, σας έχει αποσταλεί ένα link επίσης για να βοηθήσετε να διαλέξουμε την καλύτερη παρουσίαση στο πλαίσιο του συνεδρίου. Σας ευχαριστούμε πολύ.